Hey everyone, and welcome to The Explainer. I'm really excited you're here today because we're looking at something absolutely fascinating, that invisible partner sitting right between the code we write and the machines we run it on. I'm talking, of course, about the compiler. Now, we often just think of the compiler as a basic translator, right? Just converting plain human-readable code into machine language. But honestly, it's so much more than that. It is a brilliant, highly strategic editor that practically uses magic to transform our, let's face it, sometimes inefficient code into lightning-fast software. And as we'll see, this is absolutely critical when dealing with embedded systems.
To really understand why this matters, we gotta set the stakes. In the world of bare metal embedded programming, so think microcontrollers inside medical devices, car engines, or smart home gadgets, plain, unoptimized software just isn't going to cut it. We don't have gigabytes of RAM lying around or infinite battery life. We're operating in this hyper-constrained environment where literally every single ounce of processing time and memory has to be fiercely conserved. If your code runs even a fraction of a second too slow or uses a few too many bytes, the whole system could fail. And that is exactly where the compiler's secret playbook comes to the rescue.
Okay, let's dive into this playbook. Here's what we're looking at today. First, simplifying math and variables. Second, trimming the dead weight. Third, structural gymnastics. And fourth, hardware and micro-level tweaks.
Let's kick things off with Section 1, Simplifying Math and Variables, or as I like to call it, doing the homework early.
Let's look at a play called constant propagation, along with its close cousin, constant folding. Take a look at the left. We declare that our variable x equals 14. Then we run some math, y equals 7 minus x divided by 2, and so on. Now, a naive system would actually force the embedded processor to load x, load the number 14, and then perform that division at runtime. But a good compiler? It looks at this and goes, wait a second, x is literally always 14 here. So on the right side, you can see it just substitutes that known value directly into the expressions at compile time. By folding these constants together, it entirely avoids generating useless multiply or divide instructions. It just evaluates those simple equations ahead of time.
Now, what's really interesting about this slide is how the compiler handles repetition. We call this common subexpression elimination. On the left, our code calculates b times c twice for two totally different variables. And doing that math, that eats up precious processing cycles. But the compiler catches this redundancy. Over on the right, it creates a quick temporary variable, let's call it TMP, and calculates b times c exactly once. Then it just uses that TMP value for the rest of the equations. The brilliant part is the compiler analyzes this trade-off automatically. It makes sure that the cost of storing that temporary variable in memory is genuinely lower than the cost of just doing the math twice. If it is, boom, save processing power.
Building on that, we have partial redundancy elimination. This is basically just a clever variation that cleans up the duplicate math hiding inside your if-else logic paths. Check out the left side. Depending on whether I is less than 10, the program takes different paths. But look closely. Z equals x plus 4 is computed on both paths. It's totally redundant. So on the right, the compiler optimizes that code structure to ensure x plus 4 is calculated in the most efficient way possible. It holds the result in a temporary variable t, ensuring that no matter which path the logic takes, the math is never, ever duplicated unnecessarily.
Moving on to Section 2, Trimming the Dead Weight. This is all about throwing out the useless furniture.
We call this dead code elimination. Look at this clunky function on the left. There are a couple of glaring issues here that, frankly, human programmers leave behind all the time. First off, we have an assignment to variable b, setting it to 25. But b is never actually used to calculate anything else. It's just a dead variable taking up space. Second, right at the bottom, there's another assignment to b happening after the return statement. Since the function has already returned its value back to the program, that bottom code is completely unreachable. It can literally never be executed. The compiler ruthlessly slashes all this wasted space. It strips away the dead variable and that unreachable code to dramatically reduce the overall program size. In fact, if we look even closer at that last function, the compiler's optimization gets kind of extreme. The variable a was firmly set to 24, and the function just shifted that value to the left by 2 bits. Since there are absolutely no variable inputs changing that outcome, the compiler realizes this entire massive block of clunky code is 100% predictable. So what does it do? It obliterates the whole function and replaces it with a single static return integer 96. That's it. Just the number 96. I mean, imagine how much battery life and memory you're saving when a complex function is boiled down to a single static number before the device even turns on. Absolutely wild.
All right, Section 3, Structural Gymnastics. Time to start reshaping the loops. Our first gymnastic move here is loop fusion. On the left side, we have a for loop counting up to 100 to populate array A, and right below it, a second for loop counting to 100 to populate array B. Well, the compiler realizes that setting up and tearing down loops takes processing overhead. So on the right, it just merges them. It fuses those two separate loops into a single block that iterates to 100, updating both array A and array B in the same single pass. It's exactly like merging two separate errands into one single trip to the grocery store.
But here's a fascinating question for you. Why doesn't loop fusion always improve runtime performance? I mean, it seems like fewer loops would always be faster, right? Well, in embedded systems, you really have to think about memory bottlenecks. If you push too much data, like too many arrays or massive variables, into one single loop, you might actually exceed the capacity of your processor's very small, high-speed memory caches. Basically, you end up jamming the whole system as it frantically tries to swap data in and out of memory.
So the crucial point here is that the compiler also knows how to do the exact opposite. We call this loop fission. When a single loop gets too heavy and memory bandwidth starts getting choked, the compiler throws it in reverse. It takes that heavy, dense loop on the left and intentionally breaks it apart into two separate, lighter loops on the right. This makes sure the processor can easily digest the memory requirements of one task completely before moving on to the next.
And finally, Section 4. Hardware and micro-level tweaks. Welcome to the realm of the assembly wizards.
A perfect example of this wizardry is peephole optimization. This usually happens after the machine code has already been generated. The compiler looks through a tiny peephole, basically a very small window of just a few adjacent assembly instructions. It's hunting for final polish opportunities. If it sees redundant operations pointlessly moving data back and forth between memory registers, it collapses them into a single move. But even cooler, it replaces slow math operations with lightning-fast hardware tricks. For instance, multiplying by a power of 2 gets swapped out for a simple bit shift operation, which the physical hardware can execute almost instantaneously.
Then we have SIMD. That stands for Single Instruction Multiple Data. To wrap your head around this, imagine you have 4 friends who are all heading to the exact same destination. It makes zero sense for all 4 of them to drive 4 separate cars, right? You organize a carpool. Well, SIMD is basically the compiler organizing a massive carpool for your data. It transforms the code so that a single instruction from the processor operates on multiple data elements all at the exact same time.
And this brilliantly illustrates what that carpool looks like under the hood. We call this vectorization. Over on the left is our C code utilizing a SIMD intrinsic, specifically for the ARM Neon architecture, calling vad_u32 to do a vector addition. Then, on the right, is the actual resulting assembly code. See those VLDR instructions? Those are vector load operations. And the VLDR.I32? That's the vector addition. The processor is pulling in chunks of data and adding them together all at exactly the same time. It is perfectly parallel, which radically speeds up execution time for those intensive tasks.
Our final bare metal magic trick today is tail call optimization. A tail call happens when a function's very last act is simply returning the result of another function call. Let's say function f calls function g. Normally, function f would have to stay active in the system's memory stack, just awkwardly waiting for function g to finish so f can pass the answer back. But if you have the right compiler flag set, the compiler steps in and skips the middleman entirely. Since function f has literally nothing left to do, the compiler destroys the previous stack frame of f and jumps directly to g. This totally prevents memory blowouts, which you might know as stack growth, during those deep, recursive function calls.
As we wrap up today's explainer, I really want to share this quote directly from the course notes by Mihai Sima. He challenges his students with this specific project directive. Look at the assembly code and try to improve it yourself. Because here's the thing, the compiler is incredibly powerful, but understanding what it does actually empowers you. By looking under the hood of your own C code, you learn to appreciate this invisible editor. You learn how to write code that actually cooperates with it rather than fighting against it.
So, we've seen how the compiler simplifies math, trims the dead weight, reshapes our loops, and tweaks assembly code right down at the bare metal level to save critical memory and power. But I want to leave you with this final thought. If the compiler can rewrite our code this brilliantly in the blink of an eye, what other invisible systems are out there saving us from our own inefficiencies every single day? It really makes you appreciate the hidden depths of embedded systems, doesn't it? Thank you so much for joining me for this explainer. Keep learning, keep optimizing, and I'll catch you in the next one.